Hello students, welcome to my class on operating system. I am Shavani Kundu, Assistant Professor, Department of Computer Science and Engineering, Guru Nanak Institute of Technology. Today I will discuss the topic critical section and its solution with the help of Peterson's algorithm. After completion of this course, this lecture, you will be able to understand that what is critical section and how the problem of the critical section can be solved with the help of the different algorithm. So in this lecture, I will discuss Peterson's algorithm. So you will be able to understand and solve the critical section problem with the help of Peterson's algorithm. Now, first we will define what is critical section. So let us consider we have two processes, P1 and P2. Okay. Now, each processes P1 and P2 has some common code section. Like suppose there is a variable A which is initialized to 0. P1 wants to perform some operation on the A, like A equals to A, that is A plus plus, and P2 also wants to perform some operation on the variable A. That means it wants to perform A minus minus. Okay. So these two operations, the two processes wants to perform A plus plus and A minus minus, and before that there are some code segments. So here some codes are there, and after this this instruction there is another code segment. Some codes are there. So this is same for P2 also. Okay. Now, what is critical section for this processes P1 and P2? Now, the critical section is a common section between among multiple processes in which all the processes wants to perform some write operation or updation for a common variable or file or some common resources. Fine. So in this example, both the processes P1 and P2 are sharing a common variable A. What the operation they will perform? Both the processes are reading the data from the memory location A. They are performing the mathematical operation on it, and then they are performing the write operation to update the variable A. So here you can see, so we can say that this is a part, this is a common part which comes under the critical section, because here both the processes are sharing a common variable and performing some operation on it. So what is the critical section? So critical section is nothing but a set of code or some variable or some files where the multiple processes are updating that common variable or file to perform certain operations. Okay, and due to this updation, if multiple processes update the common section, so here this is a common section for both the processes, common in terms of read write operation. Both are writing on the same memory location, that's why they are common. Not common in terms of the operation, because it is for addition operation, it is subtraction operation. But why these two sections are common? Because they are reading, accessing a common memory location. So that's why this is a common section. Fine. So here this common section is accessed by both the processes, and they are performing some operation which will change the value of this variable. Now, if both the processes are performing the operation at the same time, then the data inconsistency will occur for this variable A. So here this common section is called the critical section. So this section we can say this is critical section. Okay. Fine. So critical section is nothing but a common section of code which is shared by the multiple processes, and due to this common section, if they perform parallelly, then data inconsistency will generate. Now you can see, you notice one important observation. You can observe something, that for the process P1, before this critical section, so what we can say, so this part is the critical section. This one is the critical section for process P1, and this is the critical section for process P2. before critical section, there is some section where some set of instructions or codes are written. These codes are not common, not dependent on each other. In these codes, the process, in this code segment, the process P1 is using a separate set of variables. In this code segment, process P2 is using a separate set of variables, files. Similarly, this is also a section where the process P1 performing some operation, and the operations are performing in this section. Let us write down some names. So this is a section 1. We can name it. This is a section 1 of process P1. This is section 2 of process P2. This is section 3 of process P1, sorry. And this is section 1 of process P2, section 2 of process P2, and section 3 of process P2. Okay. So what you can say that the section code written in section 1 and the codes present in the section 3, those codes are totally different. They are not dependent on each other. That means whatever the variables are using in this particular section, those variables are totally assigned for P1, that is not shared by the P2. Similarly, the variables or files which is used by P2 in this segment, that where variables are not used by P1. So those segments are not dependent segment. Fine. They are free segment. That means they can execute by their own. So those segment before the code segment, which exists before the critical section, that means S2 is my critical section. So the code segment which exists before critical section, this segment is called the entry section. So this is called, this is called the beginning. You can beginning section or entry section, whatever you can say. So we are calling it the beginning section, right? Beginning section or entry section. Rather, beginning section is better word, because entry section, that we use some other purpose also. Beginning section. Similarly, this S1 is also the beginning section. Okay. Now this S3 is called the remainder section. That means the set of code segment which remain after the critical section. So this is called the remainder section. Similarly, this is also the remainder section. Fine. So here you can see that here this critical section followed by the beginning section, that means some set of code, and the critical section followed by the remainder section. But that is not mandatory. Beginning section may be there, may not be there. Remainder section may be there, may not be there, or both the section may present for any process. Okay. Now, the main important thing is that due to this critical section, the data inconsistency occurs. So what we have to do? We have to devise certain procedure or process so that this data inconsistency will not occur in case of critical section. Fine. So before going to the details of the solution of the critical section problem, first we will discuss some basic assumption. That means there are some points which we should follow before designing any solution for the critical section. Okay. So first we will discuss some sections, some rules. So here you can see that there are two processes, P1 and P2. Okay. Now in the P1, this is the beginning section. This particular section is the beginning section, and this is the remainder section. Fine. And between the beginning section and remainder section, this section is called the critical section. Fine. Now if you want to design any solution for the critical section problem, in that case, you have to satisfy some requirements. So the requirements, the basic requirements for the critical section solution are, there are basically 3 requirements. So we are writing the, I'm writing the requirements for critical section problem. Requirements for critical section problems. So there are 3 requirements. What are them? The first one is called the mutual exclusion. The second one is called the bounded weight. And the third one is called the progress. Okay. So if you want to devise any algorithm, if you want to design any algorithm for the critical section problem, your algorithm must satisfy all 3 requirements. So what are those requirements? Mutual exclusion, progress, and the third one is bounded waiting time. Fine. So those are the very important consideration or conditions to design the critical section solution, or the algorithm for the critical section problem. Okay. Now first I will discuss what are the 3 conditions. What is mutual exclusion? The mutual exclusion condition says that if 2 processes are sharing a common section, which is called the critical section, in that case, the processes cannot execute the critical section simultaneously. They have to execute the critical section one after another. So this condition is called the mutual exclusion. Fine. So that means if there is a process P1 and another process P2, and both have a common section of code which is called the critical section, then what the mutual exclusion, this condition says? This condition says that if P1 execute this critical section, at that time P2 cannot execute the critical section. That means suppose at time T1, P1 is executing the critical section. Fine, yes. So while P1 will execute the critical section at time T1, so at the same time T1, P2 cannot execute the critical section. So if P2 wish to execute the critical section, it has to execute the critical section either at time T2, that means P2 can execute the critical section at time T2, or it can execute the critical section at time T0. Fine. So you can see from this sequence, time sequence, that while the P1 is executing the critical section, at the same time P2 cannot execute the critical section. So this is called the mutual exclusion. They are mutually exclusive. P1 and P2, these 2 processes are mutually exclusive. Fine. Now next one is a progress. Progress means once a process enters into the critical section. So as you can see, before discussing the progress, I have to discuss something, that while you will design the algorithm for the critical section problem, your algorithm must have 2 sections. First one is the entry section that decide which process can enter into the critical section to perform the solution, to complete their execution. And the exit section helps the process to exit from the critical section. That means if a process wants to access this particular critical section, in that case, first process has to satisfy the condition which is present inside the entry section. After satisfying the condition which is present in the entry section, the process can execute the critical section, and then after completion of the critical section, the process will pass through the exit section, and then it can execute the remainder section. Fine. So the progress indicate that while a process is in entry section, it must, after a certain amount of time, after a certain period, the process can enter into the critical section, and then from critical section it can enter into the exit section. So a process cannot stuck in any one of the section. So progress signifies that while you will write your algorithm for the critical section problem, you have to write down the algorithm in such a way that the process which wants to execute the critical section, the process must follow the progress. That means the process must enter into the entry section. It will wait for some time if required. Then after a certain period of time, it will go to the critical section. It will enter into the critical section. Then it will enter into the exit section and then leave the critical section region. Fine. So this is called the progress. Now the last condition for this for the last condition for the critical section problem requirements is the bounded waiting time. Now what is that bounded waiting time? The bounded waiting time says that if a process, so here you can see that in this example, while the process P1 is executing the critical section in here, the process P2, if the process P2, suppose process P2 has not execute the critical section before T1. So P2 wants to execute the critical section at the same time. That means P2 wants to execute the critical section at the same time T1. Fine. So what will happen? So once the process P2 wants to execute the critical section and if the same critical section is executed by the process P1, in that case P2 has to wait because the condition of mutual exclusion. So P2 has to wait because two processes cannot execute the critical section at the same time as per the condition of the mutual exclusion. So P2 has to wait. Now how long the P2 will wait? The waiting time for the P2 must be definite. So P2 knows that how long it has to wait. So that's why the third condition signifies that if a process waits for executing the critical section, in that case the total waiting time for the process should be finite. The waiting time cannot be infinite. So if you wish to write an algorithm to solve the critical section problem, to solve the problem of the data inconsistency, in that case your algorithm must satisfy all three conditions. So those are the basic requirements for the critical section problem, the solution of the critical section problem. So your algorithm must satisfy all these three solutions. Fine. Now next I will discuss the Peterson solution algorithm, and I will show you that how the Peterson solution algorithm can solve the critical section problem, and how that Peterson solution, that means that algorithm satisfies all the three basic conditions of the critical section. Fine. So next we will discuss the Peterson solution. So this is our next algorithm is Peterson's solution. Okay. So our objective is to satisfy the requirement of the processes so that all the processes can execute the critical section, but not at the same time sequentially. Fine. Now let us say that there is two processes P1 and P2. So we will write the name of the processes, like here it is P1 and another process P2. So make it generalized, we will write it Pi and Pj. Fine. Now the process Pi has the critical section and Pj also has the critical section, same critical section, that is common section of code which is present between Pi and Pj. Fine. So this is, we can write, this is the critical section. Pj also has some critical section. Now, as I told you that if you want to design your own algorithm for the problem of the critical section, to solve the problem of the critical section, then your algorithm must have some entry segment. This is called the entry section. You have to write down the code for the entry section. You have to write down the code for exit section. And between the entry section and exit section, the critical section will be there. Fine. CS will be there. So similarly, in the Peterson solution, to solve the critical section problem, for the Peterson solution, there is the entry section. So this is the entry section, which is present before the critical section, and after critical section, there is some exit section. Okay. So exit section should be present for both the processes. Okay. I think it is clear. So there must be some entry section and exit section for both the processes. Okay. Now, how the Peterson solution can ensure that while the PI will execute the critical section, then PJ cannot execute the critical section. How the process of the Peterson solution can ensure that. Fine. So you know that for the process PI, this is before this entry section and exit section, there is some beginning section. And there is also some remainder section. That means the rest of the code for that program. So similarly for PJ, there is also beginning section and there is also remainder section. Okay. Now, to solve the problem of the critical section using the Peterson's algorithm, this algorithm uses two variables. First one is the turn. So we will name the variable turn. Okay. And second one, a Boolean variable, which is called the flag. Okay. So if you have to remember one important thing, that this Peterson solution can solve the critical section problem between two processes. If there is more than two processes who wants to execute the critical section, then in that case the Peterson solution is not applicable for that problem. Fine. So if you have only two processes who are sharing the critical section, in that case we can apply the Peterson solution. But if there are more than two processes, in that case we cannot apply the Peterson solution to solve the critical section problem. Okay. Now here what happened, there are two variables. The one is called the turn and second one is the Boolean variable. Now the value of the turn, what should be the value of the turn? So this turn is a memory location. Its value can be either I or j. So turn can hold either the value I or it can hold either the value j. Now this flag variable indicate that if process PI wants to execute the critical section, it will set its own flag variable true. Okay. So what we will do, we will set the flag variable true for the process PI and PJ both. Okay. So we will write down the flag for process I is equals to true because PI wants to execute the critical section and PJ also wants to execute the critical section. So PJ will set its own flag of J is equals to true. Fine. So T stands for true. So while the flag I or flag J will be set to true, if the process wants to execute the critical section, then the process will set the flag true. Okay. Now, after setting the flag true, what the process PI will do? PI will set the value of the turn is equals to J. Okay, so PI will set the value of the turn is equals to J. So we will write down it more clearly. Let us delete all of them. We're writing it properly. We make a big and so let us write down those all the things once again. So before that, it is our beginning section as it was discussed. This is beginning section. This is also. So what this is for the process PI and this is for the process PJ. Okay. So PI and PJ. What we will do over here? So if PI wants to execute the critical section, it will set its own flag, that is flag of I is equals to true. And similarly, as I discussed, the flag of J will also be true as PJ also wants to execute the critical section. Now, after doing so, what the process PI will do? It will set the turn variable J. That means it is checking whether the PJ, what is the objective of setting the turn variable J? The process PI is setting the turn variable J because it wants to check whether the process PJ wants to execute the critical section or not. Fine. Now, similarly, here the process PJ also can set its turn variable I. Okay, to check whether the I is executing the critical section or not. Now, after that, what it will do? It will write down in this entry section, we will write the code like while the flag of J is equals to true and turn is equals to J, do no operation. The same is true for here. It will check while flag of I is equals to true and turn is equals to I, then do no operation. You can see we are putting semicolon after while operation. That indicates we are not doing any operation. Right? Now what will happen over here? So here you can see that turn variable is initially set to null. Now this flag variable, so there are two flags. One flag is for process PI, another flag is process PJ. So we will write down the flag of I. This is a memory location for the process PI, and flag of J, this is also the memory location for the process PJ. Both wants to execute the critical section, or both will set the value T. Now here is the main twist. That means the PI will set the value of turn equals to J, or PJ will set the value of turn equals to I. So between these two execution, both wants to, PI and PJ, both wants to execute the critical section. So between PI and PJ, any one updation of the turn variable will last for any one of the process. So let us say first PI set the turn equals to J. So the turn variable will be the value of the turn variable. This memory location will assign by the value J. Now at the next time the PJ will set the turn variable I. So the turn, this memory location must have either I or J. Both values cannot be stored inside the turn variable. So either I or J, any one of the values should be stored inside the turn variable. Fine. Now let us say for this case the turn is set to I. Now what will happen? Now both Pi and Pj will execute the next statement while flag. So here it will execute while flag j is equals to true. So definitely, what is the value of the flag j? It is true. And turn is equals to j. So what is the value of the turn? The value of the turn is I. Fine. So turn I equals to j will not satisfy. So the condition of while loop will not satisfy. So while will come out from the while loop. That means while loop will not execute for the infinite times. Fine. So we will come out from the while loop. Pi now can execute the critical section. Now we observe the same thing for the Pj. That means while Pi is executing the critical section, Pj also check the while statement. Fine. So it checks that what is the value of flag I. So flag I is true. True equals to true. So this condition is satisfied. Fine. Now next, and turn is equals to I. So what is the value of the turn? I. I is equals to I. This is also satisfied. So both the condition, that means it is true, it is also true. True and true, true. So while if the satisfy of the while loop is true, then it will execute this while loop. It will check the condition once again. That means the process Pj cannot come out from that infinite while loop. It is continuously monitoring and checking the conditions again after again. Fine. Now Pi is in the critical section. So Pi is executing the critical section. After completion of the critical section, so what the Pi will do, as it completes its execution, so it will set its own flag value. That means it set its flag I is equals to false. So the flag I will now change to false. Now you can observe, you can remember one thing, that Pj is continuously checking this condition because this is an infinite while loop. After a while we are putting semicolon. So Pj is continuously checking this condition. So what will happen over here? While as the Pj is continuously checking this condition, the Pj now the next, after setting the flag I equals to false in the next iteration, while Pj will check the condition of the while loop. So what is the value of flag I? Now value of flag I is false. False equals to true will not satisfy. So it will come out from the while loop. Now the condition of the while loop is not satisfied. So it will come out from the while loop. Now Pj can execute the critical section. So once the Pj will complete the execution of the critical section, again it will execute the exit section, and in the exit section it will set the value of the flag j is equals to false. Fine. So in this way, the Peterson solution can handle the problem of the critical section. So here you can see this is a critical section, but both the process, if both the processes Pi and Pj wants to execute the critical section, between Pi and Pj, anyone will get the chance to execute the critical section at a time. Both processes cannot execute the critical section at the same time. Fine. So this is the in this way the Peterson solution can solve the problem of the critical section. Fine. So this is our called the entry section of the, this is the code for the entry section, and this is the code for the exit section. And the code for entry section, and this is the code for exit section. Okay. Now, so next what I will show you that whether this Peterson solution can satisfy all the three requirements, all the three conditions of the critical sections algorithm or not. Because at the beginning I told you that each algorithm which we will design to solve the critical section problem, each algorithm should satisfy the three conditions. The first condition was mutual exclusion. So first we will check whether this algorithm will satisfy the mutual exclusion or not. So what is our first conditions? First condition is mutual exclusion. Okay. So mutual exclusion, as you know, as the definition of the mutual exclusion is that two processes cannot execute the critical section at the same time. So here it is very clear that while the Pi is executing the critical section, Pj is under the infinite while loop. It cannot execute the critical section. That means it cannot come out from the entry section. Okay. So while PI is executing the critical section, PJ cannot come out from the entry section. PJ is not getting entry to execute the critical section. So the Peterson solution satisfies the mutual exclusion. Next, the condition is progress. So here you can see the progress is also there. So that means first the PI will execute the entry section, fine. Then after passing through the entry section, it execute the critical section. After executing the critical section, it will execute the exit section, and then again it will execute the remainder section. So there is a progress of the process. So this condition, that means it is not stuck. That means the PI, after executing of the critical section, PI cannot go back to the entry section again. So once the process PI will leave the entry section, it has to execute the critical section, and once it will complete the critical section, it has to execute the exit section. So there is no possibility that after executing of the critical section, PI will again go back to the entry section. So that means progress is also there. So this is not there, so progress is also there. Number 3 is the bounded waiting time. So you can observe, one important thing is that in case of PI, let us say the time required to execute the entry section is T1, this is T2, and this is T3, total execution time. So once the process PI is executing the critical section, PJ has to wait. How long it has to wait? The PJ has to wait up to T2 unit of time. That means the waiting time for PJ is T2. Equals to T2. So here you can see that waiting time is bounded. There is no infinite waiting time. So it is very clear that Peterson solution can satisfy all the 3 conditions of the critical section algorithm. So in this way, we can prove that Peterson solution is an algorithm which can solve the critical section problem, which can provide the solution for the critical section problem if there are 2 processes executing simultaneously. But if there are more than 2 processes, then in that case, the Peterson's solution cannot solve the critical section problem for that. Fine. So that is all about the mutual exclusion critical section and the solution of the mutual exclusion problem with the help of the Peterson solution. Now this Peterson solution is also called the software based solution because here we are solving the problem with the help of writing a code. So that's why this solution is also called the software based solution. Fine. So that is all about today's lecture. In the next lecture, I will discuss another algorithms, which is a hardware based algorithm to solve the critical section problem.